How do you do, ladies and gentlemen, and boys and girls, and teachers, and mothers and fathers, and people, as I like to say, which suggests that the stuff I do, I like that word stuff, the stuff I do, I am of the view, has some virtue for young and old, people of all ages, in all walks of life, and of all levels of schooling. Because why? Because they are just enchanting and dramatic things to contemplate. I'm Julius Sumner Miller, and physics is my business. And my business today has to do with vibrating bars and strings. Vibrating bars and vibrating strings. Vibrating bars and vibrating strings. So consider the following. I have a bar mounted on a hollow chamber, a resonating chamber, and I shall speak of resonance subsequently. This bar is so thick, so wide, so long, and made of certain stuff, steel. And it is mounted at two very important places, fixed right there. I'll represent that bar in cross view, so, and it is fixed there and fixed there. Very specially placed fixes. Now I'm going to strike that bar. Oh, strike it. As I have already suggested, it is vibrating quite like that, but too fast, of course, to see. And it is vibrating 440 vibrations per second and emits what we call A. Although I'm led quickly to consider this, I think the European musical A is 426 or some such. You better check that. 440. Anyway. Now, here is another bar which one might view as absolutely identical with the first one. So we think, but they are not quite exactly alike. And how will I know? Let me strike this one and quiet it. Let me strike this one and quiet it. I assert that they are not quite identical. And it would take an ear possessed of perfect pitch, like Tchaikovsky or a Bach or a Beethoven or a Mozart. They could tell. I'm going to show you that they're not alike. Listen. They differ in their frequency by 1 vibration per second. Here's 440. Here's 441. And therefore, every 440 vibrations, they are out of phase and create what we call acoustically a beat. This is a destructive interference. Now, I'm going to show you this in a better way. Here is a tuning fork, so fat, so long, it is a bar bent at the middle and fixed to a resonating chamber, which is hollow, empty. No, never empty, filled with air. The box is so long, very critical, because the box must have a length appropriately resonant to the frequency of the fork. This fork emits middle C. This fork emits middle C. Now I'm going to load the prong of one of these with a load, which means that I give it more inertia. I make it fatter, heavier, more sluggish. Now listen. Listen again. Now I'm going to load it differently. Just slip that weight down further. Or I'll load it differently. Change the beat frequency. Now, I said that this bar is vibrating in this special way, but so fast we can't see it. I want to show you that that is so. I have here a bar, happens to be a metal pipe. It is so long, and I'm going to fix it with my fingers at such a position, right there, And I'm going to strike it transversely, right there, and watch what it does. Let me do it better. Let's see if we can get it on the shadow. Little difficult. Let me take another bar. Little difficult to see this. Uh-huh. How is that best seen? I'll do it again. This position is at rest. Another symmetric position is at rest. I'm going to show you that I can take hold of the bar at those nodes without interfering with the motion of the bar. There it is, bar still vibrating. Let me take another one. I'm doing this because I think it's difficult to see this on the camera, but watch it. Oh, there, that's very clear. That's a good one. And if I was a little more, there it is, bar still vibrating in the manner of the 440 and 441. Now, if I grasp it anywhere else, it is damped out instantly. A good question to ask is this. Here is this bar, which I held here, and another node was symmetrically established, and the bar then vibrated quite like that. And the question I like to ask is, how much part of the bar is this distance here? And nearly everybody says 1/4 the length of the bar, Professor. And this happens not to be right. I'm going to tell you what is right. It is 0.224 of the length of the bar, which is a very interesting thing for students to explore. Now, here I have some other tuning forks. Notice I didn't know which one was singing. I had set it into oscillation. Here is one. They are in resonance. Identical pitches, identical frequencies. Indeed, I'm going to show you something very remarkable. Let me take these two. I'm going to strike this one and stop it, damp it, and listen carefully to the response of the other. Listen. A little difficult. Some trouble. I know what the trouble is. Too loose a tabletop so that the energy is being taken up by the table rather than by the resonating chamber there. But I shall return to this. Let me go to some vibrating systems. My musical sticks. Look here. An array of sticks cut to certain length, and I'm going to drop them successively. Listen. Now, I have to tell you a little story because it's quite enchanting. One of my colleagues, having an eye to giving me some headache and trouble, put a bar in there one day, unknown to me, and I came then to play them, and you listen to the consequence. Hear that? Yeah, he fixed me by putting one in which was not quite tuned to the sequence of the others. Vibrating bars. Now, consider strings, vibrating strings. I have here a metal sliver, a little electromagnet in here which is energized by the electric current, so that this sliver is a driver of a string whose length I can change, whose tension I can change, but whose thickness or linear density is fixed. Now let me start this string vibrating. I plug in the little electromagnet. Now watch. I have a string of certain length. There we are. I have put it under certain tension. I wonder if I can improve that view of things there by maybe having a white card or a black card or something. Will that do better? That may do better. That may do better. Watch it. I'm having trouble. There we are. There's the fundamental of that string, which is so long, beautiful. Oh, fellas, you've got it okay. So long, so tight, under such tension. Now I'm going to change the tension. Yeah. Notice I'm having a little trouble. Well, that's physics. Physics is sometimes trouble. There we are. There we are. 2 loops. So for this string, this is the second harmonic or the first overtone. Let me change the tension now. 3 loops. Third harmonic. Second overtone. Let me see if I can get 4 loops. There we are. 4. No, 3. I can't count too well. There's 4. And notice how uniquely defined the nodes are, where the string is said to be at rest, but which is not quite true because some energy must pass through there, and hence there must be some motion. Let me get a very high harmonic. Very high. Well, there are 4 loops. There I have, I think, 5. And so, I'm getting a little tired because it calls for some energy, keeping that string in proper tension. I want to show you now this business of resonance that I tried to show you on the forks but had some trouble with. Listen, I'm going to strike this fork, bar, present it to this one, stop this one, and listen to this one. Listen now. That one's going, but this one isn't. I want to do it again. And this is resonance, which is exactly what happens, of course, when your ear hears me. Certain pulses reach your ear, so many per second, put the eardrum into motion. It responds very acutely, sharply. This acoustic energy is delivered to the bones in the inner ear and thence to the brain. So in the last analysis, you hear with your brain. And what you hear, of course, we hope, in the case of my utterances, possesses some meaning and some virtue. And I thank you for listening. I shall return another day. How do you do, ladies and gentlemen, and boys and girls and teachers? I am Julius Sumner Miller, and physics is my business. And my business today, making more noise, I suppose, or sound, or some such. More exactly, this business of resonance and forced vibrations. Consider the following, which I tried on an earlier lesson to do, but with not too much success, for some reason. About this, I should say more. You know already my philosophy. Experiments, demonstrations never fail. For nature to do what you want her to do, you must make some very special, meet some very special requirements. If they are not met absolutely precisely, nature will not show what you want her to show. She will do something else. So if the experiment did not succeed in an earlier case, we'll try it again. But we are forced to think of why didn't it work before. Two forks, middle C, middle C. We hope they're identical. Hollow chambers, resonating chambers. I'm going to strike this one, quiet it, and we will hear that one. Why? This emits 256 pulses per second, which are fed into this one. This picks them up and is set into oscillation. Listen now. There it is, clear as the nose on my face. I'm going to do it again in the reverse order. Listen. There it is. Now, how far apart could this be made to happen? Oh, great distances, because this is exactly what your ear does, and you could hear me at some great distance, I am sure. Resonance. Resonance. Consider now the following. I have here two cardboard tubes, one of which slips inside the other, so that I can change the total effective length. I am going to strike a tuning fork and hold it in front of this open pipe, which is so long, which has a certain natural frequency. I'm going to change the length by this sliding tube and hope to find a resonant length for this fork. Listen now. Yeah, there is a place. There is a place at which this length is resonant to this frequency. That's an open pipe. This end is open, that's open. Here is a closed one. Now, it would be an interesting exercise to compare the lengths of open and closed pipes for the same fork, but I leave that as an exercise for you. This is closed because it is closed on the bottom at the table. Listen. Uh-huh. Let me use another fork. This fork happens to be what? 512, that's an octave above middle C. Oh, I can't get a length there. There it is. There it is somewhere in there. Let me try this open one. Very clearly resonant, very clearly resonant. Or, as I might do it, consider here. Here is a glass cylinder with some water in it and a lucite tube, and this is a closed end, so the air column here constitutes a closed tube. Let me show you resonance. There it is. Now, what can one do with this? By making certain measurements, we can determine the velocity of sound in air. Here is another tube, another fork. Oh, very clearly resonant. I hope if the tube is long enough to find another resonant length. Listen. Yeah, pretty nearly. I couldn't quite make it with the lengths available to me. Resonance, resonance. I want to show it to you in a more delightful fashion. Here is something really enchanting. A wooden frame, which is hollow, so like the belly of a piano or of a fiddle. A tightly drawn string with two bridges, one here and one here, so that I have cut off a certain length of string this long. The string, therefore, has such a length, is under such a tension, and is so fat. Now that string has a certain frequency. Listen. It therefore has a certain pitch. It is resonant to a certain fork. Proof. I've put a little paper rider on there, because if the string is vibrating, you can't see it. And I'm going to strike a fork and apply the end of the fork to one of the bridges And we hope that the energy of the vibrating fork is communicated through its stem to the string. And if the string is vibrating, we would hope to see the little flag there quiver. Watch it now. Oh, yeah, I like that. Let's get tight on that again, boys, because I like that. And do you see, people, if I like something, well, I might do it again because I like it, and that's good enough reason. Mark you, I suppose I have done this demonstration 4,782 times, and it never fails to stir my soul because it is pretty and dramatic and spirited. Watch it now, watch. Ah, there it is. Now the question is, will this string respond to some other fork? That would happen to be B, 480. Let me try 384, which is G. Listen, watch. No. That string can vibrate 480 times per second in a natural, ordinary, comfortable, happy way. It will not vibrate 384 times per second. How about 426.6? Oh, yeah, that reminds me. I find a fork. On an earlier lesson, I suggested that, I said that A in America, the orchestral A, was 440 vibrations per second. And then I said that I thought that A in Europe was 426. I find it, 426.6. Now listen, watch. No. But 480, yes. There it is. And so we have that kind of behavior of vibrating strings. Consider now the following. Let me get this out of the way. A fork. I strike it. I deliver the stem of the fork to the table. What's happening? The table is being put into oscillation at the same frequency as the fork, which is 426.6. But the music it emits, the sound that emerges, has a little different quality to the ear. Sure, A, when played on the piano, sounds different from A played on the fiddle. So this has a different quality. But the table is forced into vibration that many times per second. Let's take 480. Listen. Let me try this table back here, which has more stuff on it. May have higher or lower pitch, I don't know. Very interesting. Now something quite enchanting. Consider the human voice, which results from the vibration of the vocal cords, the hollow cavity called the mouth, where the tongue is, where the teeth are, how the lips are held. That chamber, the vocal chamber, has a resonant frequency. And I have observed over the years that when I try resonance at the open mouth of boys, the response is to a fork of lower frequency than that for girls. Let me show you what I mean. Listen. Well, let me try another fork. And sure enough, this is 426 and that's 480. Let me try one lower, 384. Maybe I'm boom, boom, boom in pitch. Let me try a higher one, 512. Notice I have a strange vocal system, resonance, forced vibration. In certain places in the country, in New England, there are some wooden bridges still with signs fore and aft that say, no trotting of horses on this bridge. No trotting. Why? The periodic delivery of forces from the horse's hoofs might set the bridge into vibration and render it apart. Or consider soldiers in marching, crossing a bridge, they break up their stride. Now, where do we have some ancient, wonderful commentary of the same sort? If you read Joshua in the Old Testament, Joshua 6:20, it says something like this: the priests blew their trumpets and the walls fell down flat. And I've often wondered why the sackers of cities didn't just go around the world, the then known world, with bands and musicians playing music in order to fell the walls of the cities instead of attacking them with manpower. All right. Resonance, forced vibrations. Consider this, which is quite enchanting to look at. Here I represent the towers that carry the big, heavy cables in transmission of electric current across the country. This is a cable. It might be viewed as hanging like this. The shape in which it hangs is very special, incidentally. It's called a catenary. And if you look up the word catenary in a dictionary, you will find that it means chain. Now, when the wind is very high, this cable could be set into oscillation, which is dangerous for the mechanical system, as well as for the electrical affairs. Problem, we need to damp out that mechanical motion. And so what is done? If you look closely, next time you see these transmission lines, you will observe that there hang on the wires some system that looks like this, called a damper. Now what happens? When that cable is set into vast oscillation with large amplitude by a stout wind, the cable, having flexibility, as I will show you, takes up the oscillation and damps out the mechanical motion of the wire. Here it is. Here is a cable damper. The wire goes through there, and now you see these are flexible, and this takes up the energy of the oscillating wire. So I say this business of resonance, forced vibrations, mechanical damping, and the like, very enchanting to contemplate, and I would invite you to think more about it. So, more on resonance, more on forced vibrations. Mark you, all this evidence that the natural world presents to us is gotten by one of our senses, namely the auditory, and all governed by the reception that the eardrum gives to the variations in pulses. And I thank you for watching. How do you do, ladies and gentlemen, and boys and girls, and teachers? I'm Julius Sumner Miller, and physics is my business. And today, some very enchanting business in this business of sound. More exactly, some sounding pipes, singing pipes. Some mechanically excited, some thermally excited. All very, very exciting. And I hope you will engage in it yourself. Consider the following. Let's look over here. I have a box which I call a wind chest. It is a tight-fitting box with a nozzle here so I can blow some air, and some holes in which I can fit a pipe. Now, these two pipes that I have are of identical length, and I'm going to blow them with some air, and they should be in resonance and sound alike. Watch this now. They are in resonance. Now I have on this one a sliding sleeve, which allows me to change the length of the pipe. If the length of a pipe is changed, its natural frequency changes, and the pitch it emits changes. Now, if then I have two pipes emitting different frequencies, we should have, at certain symmetric intervals, a thing we call beats, which you will hear when I change the length of this pipe with a sliding sleeve. Now listen carefully. Listen. The greater the difference in length, the greater the difference in frequency, and hence the greater the number of beats per second, or the beat frequency. So I change the pitch of one of these pipes by changing its length. How else can I change its pitch? Answer, by changing the density of the medium with which it is blown. I can do this in two ways. Supposing I heat the wall of this pipe. The air inside is heated, the velocity of sound increases, the pipe changes in pitch, and we should hear beats again. I'm going to play a burner on this pipe, blowing it. Listen now. Now I'll bring the other one into resonance with it. There we are. There we are. The beautiful behavior of singing pipes and their pitch changed by changing their lengths and their the thermal properties of the medium. Now consider this. This will enchant you absolutely. It's going to enchant me because I'm going to have some trouble. I have here a metal pipe, two metal pipes, with a wire screen inside. Here is a piece of screen the like of which you have in your window. I have lodged a bit in there at a certain position. Now these two pipes are of identical properties except their length, one longer than the other. I'm going to heat the screen in one of these pipes. Listen now. Oh, that is fantastic. Now I'm going to heat the screen in the other one, which is a longer pipe and should have a lower pitch. And as I'm led to say, having filled it with music, the music can't fall out when the pipe is like this, but watch me. All the music fell out, so I'll fill it with music again. I'll fill it with music again. And I say it can't fall out like this, but it can when I turn it up. There it is. And I think that's wonderful. Now, if they have different natural frequencies and I excite them together, we should have this mechanism called beats, which I will give you evidence of forthwith. Listen. Beats. Wonderful. Now, here I have another such pipe, longer, well, again with a piece of wire screen, and if I don't run into any trouble, I'm going to fill this pipe with music. We should see the whole length of the pipe. Listen now. Is not that an amazing acoustic life? Listen. Incredible. Now I have one a little longer. Listen. I fill it with music. Now I should tell you, parenthetically, that the physics of thermally excited pipes very difficult. Very low. Another one longer still. Like the steamboat on the Mississippi. Notice how long the acoustic life. Incredible. A longer one still. Listen now. Listen. That's more like the steamboat on the Mississippi. And there the music can't fall out. Now I hope the rest of it will fall out. I think this is terrific. Thermally excited pipes. Now these are metal pipes, and they have a wire screen in them. Let me show you what it looks like here in a sketch. There is the pipe, and there is a screen put in there in a certain position which you can get experimentally. Now, metal pipes with a wire screen, and you observe that, oh, that's a little hard to handle. You observed that this pipe emits its music after I remove it from the source of thermal energy. I'm absolutely enchanted how long this lives. Notice, we may do the whole show on this one pipe. Remember, metal pipes, wire screen, they sang, as we say, after they were thermally energized. Now a new business. Oh-ho! I have here a cardboard pipe, the like of which rugs come rolled on. And as I am always given to ask a student, look inside. Nothing in there. Right, he says. Wrong. Filled with air. Watch that. Now watch this pipe. No screen in there. Watch it. Uh-oh. Pipe so long, such a natural frequency. A longer pipe, lower pitch, and a longer pipe still. Now, I'm going to have to try something that requires a little astute doing here. I have a very short pipe, but very large cross-section. Nothing in there except air. No screen, cardboard. I'm going to try to excite this. Calls for very special doing. It may not work. So then don't forget, don't you ever say, Professor, it failed. No. I do not have maybe the right requirements for nature. Let's try it. You'll notice that I am supplying much more thermal energy for a bigger volume of air. Listen. Uh-oh. I'm in a little trouble, so we'll just take a little more time. We'll just take a little more time. I'll try it once more. No, I don't have enough heat energy there. Let me try one more. Shorter. But since I have a moment or two left, I want to go back to some of these because I think they're terrific. I hope you see, ladies and gentlemen and boys and girls, that I am having much abundant fun, which is the only reason, really, why I'm doing this. Because I'm too old to work for any other reason. Just fun, that's all. I am stubborn enough to want to try this again. I'm going to turn up my heat. No, having a little trouble, not the right heat energy. Let me try one more of the metal ones. Notice, I'm filling this with music. It is not singing while being energized. Now it is. I say that is quite like a sacred hymn. Very quiet and peaceful to my soul. And so, what can you do? Go to a junk shop, get yourself some metal pipes, take some screen, window screen. If you can't get any anywhere, cut some out of your window. Take a glob of it, push it up into the pipe, get a burner or a blowtorch, and you have singing pipes with much delight and enchantment and abundant fun, which is really the greatest virtue to be gotten from study, intellectual fun. And I thank you for listening. How do you do, ladies and gentlemen, and boys and girls, and teachers? I'm Julius Sumner Miller, and physics is my business. And we have been doing some exciting and dramatic inquiries into the nature of sound, its properties, how it's produced, and such. And our business today, vibrating rods and plates. Now, we have already looked at a rod vibrating transversely, that is, in such a manner. Now we are going to behave a little differently with a rod. We are going to excite it longitudinally or compressionally. Here is a metal rod, certain kind of stuff, so long, such cross-section, and I'm going to hold it at successive places, here and here and here, meaning that I am changing the position of the nodes on the bar. But rather than exciting the bar transversely, I'm going to excite it longitudinally. Now listen, listen. And somebody says, well, I can't get excited about that, Professor. No, not much excitement there. But watch now. I'm going to change the position of my holding hand where it is damped. Aha! Altogether new life and spirit. Watch it. Different still. Notice how quickly it damps out when I grab it elsewhere. Oh, that's a high-pitched one. Listen now. Listen. Oh, man, that's up there. And look how long the acoustic life. Man, that's up there. Incredible. Bar is emitting several harmonics simultaneously. The wonderful behavior of a bar excited longitudinally. Let me take another one that has different cross-section, different length. Listen. I hear some beats, a remarkably difficult thing to understand. Notice, a high-pitched one amidst the others. We say that these bars have a high Q, which I have little time to explore, meaning that I put so much energy into it, so very much of that comes back to me. Vibrating bars. Let me go now to something most dramatic. Vibrating plates. Oh, an enchantment I'm sure will delight you. And for this, I get down here in a sort of prayerful mood. And what do I have? I have a metal plate, brass. It is so big, so thick, fixed to a shaft, centrally and tight. Now I'm going to bow that plate with a bow. Remember, to have a sound, we need a vibrating system. The plate is vibrating. But how? You can't see it. It is vibrating too fast. So I'm going to sprinkle it with a little sugar. Sugar, in order to sweeten the sound. Sugar. Sprinkle it with a little sugar. And now I'm going to bow it and watch what happens. I say that's very pretty. I say that's very pretty. Now let me bow it in another place. Stay right there. Stay right there. I bowed it in another place. The sugar is a little sticky, I'm afraid, because it is damp and it has taken up some water. Let me bow it again. That's what I had first. Let me bow it another way. I'm having a little trouble with that plate. I don't know why. Let me take another one. Another one. Different size, perhaps. Different material, perhaps. Let me bow this. Oh, I say that's very pretty. Let me bow another rectangular plate. These, by the way, are called Chladni plates. Capital C-H-L-A-D-N-I. Chladni showed these to Napoleon. And what did Napoleon say? Professor Chladni makes musical sounds visible. Now, who would believe that there could be seen anything pretty on this plate? But I'm going to sprinkle it with some sand, and I'm going to bow it in the middle. And this is what I got before. So what the plate does, how it vibrates, is governed by its size, shape, nature of stuff, how it's fixed, and how I bow it, because I'm going to bow this in a different way. Watch. And I say that's very pretty. Now, what will a circular plate do? Aluminum, centrally fixed. Oh, let me bow it without anything on it. Notice in the first bowing, I overbowed, excited, and harmonic. So I'm going to sprinkle it with sugar, sand, and bow it. And I say that's very pretty. And you notice I have a six-starred figure. Here is a smaller plate, aluminum, fixed again centrally, the same thickness as the other, but because it's smaller, it should have a higher pitch, less inertia. Very pretty. Now let me bow this one with some stuff on it. Oh, that's 6 again. Let me try to get 4. Oh, I'm getting 8. I'm getting 8. 3, 5, yes, I'm getting 8. Let me try to get 4. You notice what's happening. 4, 6, 8, 12. und so weiter, and so further. Not so well defined. That's well defined for 6. I'm going back to this other one to see if I can't get 4. Yeah? There. 4. So we have the wonderful investigation of Chladni plates and Chladni figures. Let me go back. Vibrating bars and plates. Point of view. Here is a goblet, a glass. Is that a vibrating plate? Sure. It's a plate that has been folded up and it has some acoustic properties. Now, what have I done? I filled it to a certain depth of water. There is a certain measure of glass that's free of the damping effect of the water. And you know what we do. We stroke it, and listen. Listen. The same kind of glass, differently loaded. Another kind of glass, different depth of water, different resonating air chamber, different wall thickness, all together. Now, different glasses still, sherbet glasses, I guess you call these, or some such. Now, what could we do with this? Could we not have an array of 8 of them, say, and tune them to the major diatonic scale, and with some skill, play these goblets and make music? More on vibrating plates. A piece of a steel drum, such as oil or gasoline or the like, comes in, a piece cut off, and then it is shaped. And you have all heard the steel drum music, which has some beautiful acoustic properties. Now, how is this done? Well, the plate is simply indented at various places, creating plates of different size, different tension, and different thickness. And so here we have it. What I'm pointing out here is, without playing any music, you see my incompetence in that, is to suggest that all we need is some system put into oscillation, put into vibration, so that it delivers compressional pulses in the air, which are then brought upon the ear by propagation in the medium. Next matter, a tuning fork. A tuning fork. I should have a striker. Why? Very bad to hit it on something hard, it deforms. This fork has a natural frequency of 512 vibrations per second. 512. So when this fork is at rest in my hand, there are 512 pulses reaching my ear, reaching the microphone, reaching your ear per second. The fork is vibrating, the prongs are, but the whole system is at rest. Now what am I going to do? I'm going to excite the fork and swing it on the end of a string like this. And what will you hear? As the fork approaches you, you will hear a rise in pitch, and as it recedes from you, you will hear a decay in pitch. And this is known as the Doppler effect. D-O-P-P-L-E-R, the Doppler effect. Very essential matter, both in sound and in light. In light, it plays this role. We can tell from the spectroscopic analysis of stars whether they are going away from us or coming toward us, according to the shift in the frequency. Listen now, listen. And this has much to do with your behavior on the highway, because when you hear a siren approaching, If it's from behind and you've decided that it's already police, you know how the pitch rises as the vehicle approaches you. If now the pitch decays at a gradual rate, this means the vehicle has passed you by. But supposing that which you hear comes to instantaneous rest when the vehicle that's sounding is close upon you, I am led to say in the vernacular, you've had it, which is a very good description of the behavior of Doppler's principle in your life. And I thank you for watching. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And we come now to another lesson in the dramatic subject of sound, and this one possessing some uncommon enchantment. You remember, I hope, that I have considered plates fixed in the middle and bowed with a bow, and certain figures result due to the behavior, the mode of oscillation, vibration of the plate. And we call those plates Chladni plates, capital C-H-L-A-D-N-I, and the figures that result when the plate is bowed, Chladni figures. Now, a little different matter. I have a rigid support from which I fix two strings in this manner, and at their common junction, a third one, and hanging remotely at the bottom from the third one, a funnel, in which I put some sugar or sand or salt. This physical arrangement is known as a Blackburn pendulum, after a Scot by the name of Blackburn, and it has marvelous vibrational properties. Depending upon the lengths of these strings, the length of that string, and this distance here, a matter which calls for some mathematical exploration, and I won't go into that. But if now I draw this pendulum bob aside, having filled it, say, with salt or sugar, it oscillates in a very pretty way and makes some figures which are called Lissajous, L-I-S-S-A-J-O-U-S. Lissajous figures after a Frenchman who made an exhaustive study of them. So let's go over here and see this Blackburn pendulum generating the Lissajous figures. Here is a framework, looks rather like a guillotine. Here are the two strings symmetrically fixed. Here is the junction of the third, and this bob I could move up or down, making this length less or more. And I'm going to fill this funnel with some salt, keeping my finger over the open end. I have, by the way, put some lead weights around this funnel to make it heavier, to give it larger inertia. Now I'm going to draw this off in some arbitrary way and let it go. Now watch what happens. I say that's beautiful, beautiful. Now its motion is damping out, that is, getting less and less in amplitude, and notice the pretty figure that results. Now, let me fill it again. Let me fill it again. And let me change this position. Oh, I may have a little trouble here. I need several hands. Let me change the position. There, I've gone way up there. Well, no, with only 2 hands, I can do just so much. So let it slip out. No hurt. Okay. Now I'm going to start it again in another position. Watch it. We should, I suppose, get rid of this figure in order to see subsequent ones, but you'll get the idea. Well, I'm having a little trouble, perhaps because the framework has some motion in it. But anyway, these are very pretty things to see, and I want to show you what can be done with this apparatus. Instead of having a funnel with sugar or salt or sand in it, let me have an enormously heavy ball with a hole in the ball and a light lodged inside the sphere, the ball, so that a point source of light falls on paper. This paper I could have on the turntable of a phonograph. So the table turns, the ball moves, and the light describes some beautiful curves. Let me show you some. They are absolutely enchanting. Here's one. Look at that. This is a Lisieux Zoo figure made by a heavy bob with a light inside. Here is another one. And they are absolutely enchanting and of highly artistic composition. One would hardly imagine that these can be done by so simple a mechanical device. Look at that. Oh, here's one that I nearly missed, which would be a shame, really, to miss. This one needs to be viewed more properly that way. Or one such. Look at that. Or, look at this one. Incredible designs. Or such. Incredible. Oh, let me turn that so the camera gets a better view of it. And finally, such a one as this. Beautiful thing to witness. Now, one of my students of earlier years made such a device, and instead of having a funnel with sand or a ball with a light, he had a heavy ball with a pen attached. And the pen moved, and the paper moved. And here are some of the figures that resulted from his work. Notice the beautiful composition. Yeah. I'll run through these quickly to suggest the beauty, the artistry that can result from such an investigation. Lisieux figures. Compounded harmonic motions. Lisieux figures. Very dramatic. More to our business. I have here a glass tube in which is lodged some very fine cork dust. And here is a metal rod which I have clamped at the very middle. Half of the rod is in the glass, nearly, the other half beyond the clamp. And on the end of this rod is a piston. I'm going to draw that for you. Here is the glass tube. It is stopped up on this remote end. Here is the rod inside. It is clamped about there, and it has a piston right here. I suppose this is the piston rod, and yeah, that's piston. Now what have I done? Some cork dust, metal rod. I am going to stroke the rod with a resined or rosined cloth so that the cloth grips the rod and lets go, grips and lets go, quite like a violin bow grabbing and letting go of a string. We call this relaxation oscillations. You can do this sometimes with a cane. You push the cane on the sidewalk, it skips and grabs and skips and grabs. Relaxation oscillations. And what will happen? A compressional pulse runs down the rod, which is shaking like this, bounces off the end of the piston here, reflects from the cork stopper, and if things are right, we see the cork dust gather in very sharply defined little places, and thus we could determine the velocity of sound in this metal rod. Let us get a view of that. Let us get a view of that. Cork dust, rod, watch. We have to get tight on it. It's a little difficult to see. Perhaps a camera can get another view of it. Oh, there is some motion there. I'm getting tired. That's hard work to do that. Now, what did I say we could do? With this, which is known as Kunsttube, K-U-N-D-T'-S, we can determine the velocity of sound in the metal rod, or we could put some unknown gas in here, or a known gas, say carbon dioxide, and determine the velocity of sound in the carbon dioxide. One more demonstration. I have suggested that an acoustic wave is a compressional wave that advances from here successively through the air and falls upon your ear. To represent the advance of such a compressional pulse, I have here a little rig which I could name a wave machine. Here are two strings supporting the ends of a little bar magnet. There is a bar magnet, many bar magnets, and they are so aligned that their like poles are adjacent. Now, magnetically, you know, magnetostatically, like poles repel. I'm going to remove one, let it fall upon the others, and watch the compressional pulse advance. Watch it now. There it is. And watch it now reflected, and here it is. This reflection from an open end, a very important idea in physics. Let me suggest it once more. Right. I return again. Yeah, I returned once, so I return again to this subject of quieting an electric cable which is swinging too much. This one that I have shown on an earlier lesson is an American design. Very useful physics. I have here one made by the Germans of a little different design, and a third one made by the Swedes. And you see the cable goes through here, and this swings like that and like that, taking up the energy of the cables. One more sound producer. Notice how absolutely simple and trivial the subject can be. A piece of masonite, a prismatic slab fixed to a string. I think it is called a bull roarer. All I'm going to do is swing it around like this, and it's going to make a sound. And if you have seen some of the earlier lessons that I have done in physics, you will recall Bernoulli's principle, which is why a flag flutters, which is why this does what it does. Listen. A bull roarer. And it seems appropriate because the subject is so absolutely enchanting to show you once more a vibrating plate, which I will do with all speed. A plate which I have sprinkled, and I say that is very enchanting to see. And I thank you for following our discourse on waves and sound. Let me show you one more. Let me show you one more. I sprinkle it. Now. And this is beautiful for you to remember, and I thank you once again for following our discourse. How do you do, ladies and gentlemen, and teachers and boys and girls? I'm Julius Sumner Miller, and physics is my business. And my special business today is entitled Electrostatic Phenomena, Foundations of Electricity. The experiments I will do are absolutely trivial in their nature, but absolutely profound in their meaning. Consider the following. In the 5th century BC, a Greek by the name of Thales made an utterance of this sort. If amber is rubbed, it acquires the property of attracting unto itself light bits of straw and dust. And would you believe it, this was the beginning of all that we have in electricity and magnetism. As an illustration of it, here I have a hard rubber rod. I am handling it so that it is, as we say, electrostatically neutral. No excess charge of any sort. Identical numbers of positive and negative electricity. I approach it to some cork dust. I approach it, and we see nothing happen. Nothing. Nothing. Now, that nothing is a very significant thing. Indeed, when experiments reveal nothing happening, they are often regarded as failures. But I must remind you, a classic in our history, when at the turn of this century, Michelson and Morley did a famous experiment on the so-called ether drift. The results they got were nil, and they thought the experiment failed. But the genius Einstein took a hold of that so-called failure, and out of that was born relativity. So let's go back. The rod is electrostatically neutral. There is no interaction between the rod and the cork dust. Now I am going to do something. Trivial, really. Piece of fur. The rod has acquired astonishing electrostatic properties. Watch it now. Watch it. I approach it to the cork dust. Ho, 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 ho! Cork dust is gathered. And if we can look closely, very closely, we see an astonishing thing. Let me point out on the blackboard, on my writing board, what we really have seen. There is the rod. There is some cork dust. The rod did nothing to the cork dust in the beginning. Then I charged the rod. By the mechanical action, I separated charges. So the rod has, by definition on it, a negative charge. And you notice I'm making many negative charges on the sharp point. Very significant. Charge density is greatest at sharp points, and we shall later learn that's why Benjamin Franklin suggested pointed rods for lightning arrestors. Now what happened? Some of the cork dust got pulled up by actions I will not trouble you with here. So here's the cork dust on the rod. Then after a moment, what did we see? We saw the cork dust jump away. Jump away. That's the significant thing in two parts. One, it was first attracted to the rod. Two, after a moment, it jumped away. I'll not annoy you with any discourse on the physics. This you can explore in the classroom. Consider now a comb, electrostatically neutral. Let me bring it near some paper, little bits of paper, some confetti. And we see nothing happens, nothing. Now, let me rub that comb through my hair. Mad physicist's hair. Watch it now, watch it. Oh, notice, I must either be lifeless or of low voltage. Let me try this on here. Oh, why didn't this work? I think I know why it worked, why it didn't work. My hair is a little damp, and water vapor is a very, very bad insulator. It's a good conductor. So, watch it now. Ha-ha, there we are, there we are, there we are. Some of the paper. A wonderful experiment which you can explore in the classroom. Now, we define the charge on the rubber rod rubbed with fur as negative. Similarly, if we rubbed a glass rod with silk, we would define the charge on the rod as positive. This is a point of departure. Now, I have an instrument called an electroscope. Let me draw it for you. a metal rod, a metal knob, a metal knob, a metal rod, and a sliver of light gold foil right there. Now, I am going to make this system electrostatically neutral. Notice I'm having a little trouble. The charges are so abundant here. The gold sliver lies close against the metal rod. Now I am going to rub the rubber rod on the cat's fur and approach. Watch. What? Ho ho, ho ho. I'm going to turn this. I think this will show better here. There it is. There it is. There it is. And the nearer I get, the greater the electrostatic forces. Now, I'm going to deposit some of this negative charge on that electroscope knob, and the electroscope is permanently charged. Except that, if you will give me your undivided attention, except that the charge will diminish as time goes because of radiation that produces ionization in this room. The charge will, as is sometimes said, leak off. Now that electroscope is charged negatively by conduction. Conduction. Negatively by conduction. Question, what can I do with it? I can determine the nature of an unknown charge. I don't know what the charge is on this comb, but watch what the electroscope does. Watch it. The leaf diverges further, and by a little analysis, I could decide what the charge on the comb is. Now, I have charged, oh, notice, this is amazing. I am excessively charged myself, which means that I am now high voltage. Oh, that's a good one, isn't it? High voltage. I have discharged the electroscope again. Remember, when I made contact, I said that the electroscope was charged by conduction. Now I'm going to charge it another way. Watch. Watch. Rubber rod, negative. I'm going to bring the rod near the knob. The leaf diverges. The leaf diverges. I'm not making any connection. Now I am going to ground the electroscope. The leaf collapsed. Pretty nearly. Now I'm going to take my hand away. Now I'm going to take the rod away. And you see that the electroscope is substantially charged, and the charging this time is by induction. And I'm going to tell you, for your own edification, that when I charged the electroscope by conduction with a negative rod, it had a negative charge on it. When I charged the electroscope by induction, it had an opposite charge. That is, it's now charged positively. I'm going to prove that. Watch. Proof. Watch it. Notice the leaf collapses. That proves to me that the charge there is positive. Now, another very dramatic thing. Here I have two little wads of paper. Can they be seen? Maybe seen better over here. Maybe seen better. Where are they? Yes, two little wads of paper. They are electrostatically neutral because I have touched them and grounded them. Now I'm going to approach them with a charged rod. Watch what happens. Watch what happens. I'm going to approach them with a charged rod. They will make connection with the charged rod because of induction. They will instantly acquire a charge like that on the rod. And watch their wonderful behavior. Watch it now. Watch. Watch it. There we are. They made instantaneous connection, and now they are rushing away with all fright from their kin, since like charges repel. Look at that. Isn't that fantastic? All right. Now, I have shown you how to charge an electroscope by conduction, how to charge an electroscope by induction, and the wonderful behavior of charges plus and minus, or positive and negative. Question. In a lightning storm, charge arises in great abundance on clouds and on the earth. A good protection against electric fields, which arise from great charge density, is the following. You remember, when I have this electroscope, or one such, here is another one, with a leaf on it. If you get closely, you'll see there's a gold leaf. There it is, there it is. There it is. There it is. There it is, right? Now, that electroscope suffers the influence of this electric field produced by this charged rod. How can I protect it from these stray fields? Answer. Here is a wire cage. A wire cage just made of window screening. I have put an electroscope in here, and it matters not how intense the electric fields outside, the region inside would be a field free. And hence, where would be the safest place in a lightning storm? In a steel railroad car, or some such. Something for you to think about. Now, another dramatic experiment to show you the enormous forces that arise when bodies are charged. Here I have a slab of wood. It could be as big as a 2x4, or a 6x8, or a 12x20, and 100 feet long. I have set it nicely in balance on a watch glass. Piece of dry wood, so that it's free to move in a horizontal plane. Now, what would I do? I am going to charge the end of this stick in such a manner. Somebody says he looks like a mad physicist. Yeah, sure. I am doing some work and thus separating electric charges so that the wood now has on its surface one kind of charge and the fur the opposite kind. Now I'm balancing it again, and I'm hoping, of course, that the wood is a poor conductor. Otherwise, I would have grounded it by handling it. Now I'm going to charge the metal, the rubber rod, and watch. Watch. Watch closely. Oh, somebody says it ain't turning, which I had expected it to do. Why? The experiment failed. No, you know I'd blow my stack with that refrain. It did not fail. Apparently, friction is too great here, and the electric force is too small. But I urge you to try it. It is very dramatic. A 2x4 can be moved by the strength of the electric field produced by a charged rubber rod. So, coming back to our beginning, all I have done is rub some stuff with some stuff, and thus giving rise to a separation of charges, and thus the foundations of all electrical phenomena, which makes everything we have today possible. Merely these charges arising from the confluence of different materials. And so I thank you for your attention, and I shall return another day. How do you do, ladies and gentlemen, and teachers, and boys and girls, and mothers and fathers, and people? I'm Julius Sumner Miller, and physics is my business. And our special business today, adventures with electric charges. Adventures. Some wonderful things, really. Consider the following. Here is a slab of lucite. I've now handled it abundantly. It is electrostatically neutral. Here is a metal plate on an insulating handle. It is electrostatically neutral. I lay the plate on the slab, and I lift it, and all I'm lifting is the weight of the plate. Now I'm going to do something. I'm going to do some work on this slab of lucite. I am slapping it with a fur. I have endowed that slab with some strange electric properties. Proof. I'm going to put the metal plate on the slab, and I'm going to put my finger on the upper surface of the metal plate, and then I'm going to lift the plate with ever so great a delicacy. Correction, a delicateness. Oh, it's very heavy. There are some electrostatic binding forces, Coulomb forces we call them, and I'll show you that I have some electric energy in this metal plate, or on it. Listen now. There was a discharge. There's a discharge. There is a discharge, and I can continue to take electric energy from this system forever, which is a very long time. Indeed, the electric energy available to me there could light a fluorescent lamp, which it may be difficult to see, but that's all right. I assert it will excite or light the lamp. Yes, I saw it. It's a little difficult in the studio with these much lights. Here is a tube called a spectrum tube. It contains some neon gas, and it takes about 5,000 volts to excite this tube. I'm going to show you that I can flash that tube. Watch it. There it is. It flashed. It flashed. So, the electrophorus, that's what that is called, an electrophorus. First put together by the wonderful Alessandro Volta in Italy, Como, Italy. Now some more on these matters, adventures with electric charges. I have here a Van de Graaff generator, and here I have a tube in which I'm going to put some cigarette smoke. Getting most of it in my eyes. That tube is filled with cigarette smoke. I'm going to connect that tube to this Van de Graaff generator, which can supply me with a large difference of potential. Watch the smoke. Watch the smoke. Will you just connect the generator for me, please? A moment. There, you see it. Thank you very much. There was a precipitation of the smoke in this flask, in this tube, which suggests that the smoke was possessed of, made up of charged particles. Now I'm going to discharge that Van de Graaff because it could be a little risky for me. Let me show you something more wonderful still. Here is a three-pointed vehicle, like a lawn sprinkler. Notice the arms are bent at right angles to themselves and sharply pointed. I'm going to put this on the Van de Graaff. The system is at rest, and we will in a moment energize the Van de Graaff, and you will see an astonishing thing. We hope that little spin wheel thing will turn. Watch it. Let me have it, please. There it is. There it is. Turning. Thank you, sir. Notice there was not much charge on this sphere of the Van de Graaff generator. Now, why? Because sharp points are good lightning arrestors, or they speedily discharge the charge gathered, which tells us why lightning arrestors are sharply pointed. Consider this, which I call the mad professor's head. Some bits of paper. I'm going to make connection with the Van de Graaff. Every little sliver will acquire the same charge. And what should they do? Watch it now. Just a minute. Hold on. Will you please energize that machine for me? Look at there. Look at that. And notice, too, thank you, sir. Notice down there, the field is so strong as to be felt at a distance. Let me have that once more, because I like it. There it is. I think that's wonderful. Thank you. I'm going to try it once more. Hold on, hold on. I'm going to present my own head there, and I hope you will see the hair stand on end. A little, please. Oh, yes, I feel it. Oh, that's enough. Notice, we nearly had a disaster because I felt a discharge. One more matter. Here I have, notice how cautious I am. Here I have a candle flame, and nearby it a sharp-pointed rod, and nearby it on this side a spherical conductor. And I hope you see those very clearly. And I'm going to suggest the following. Here is the flame of the candle. There is the flame of the candle. Thermal energy gives rise to ionization. There are then, in this flame, produced by the flame, some positive ions and some negative ions. If I have the sharp point of a conductor, which is connected with the Van de Graaff, supposing there is an abundance of positive charges here, and this Van de Graaff is negative, do you see what's going to happen? The flame will be dragged over. On the other hand, if we change the charge on one of these, the flame will be pushed away. I'm going to connect to the Van de Graaff, and watch now. Wait, wait. I have to make connection. I have to make connection. Here I'm making connection with the rod near the flame. If you will energize that, please. Watch it. Oh, we had a little trouble. Thank you. I had a feeling that the flame was pushed away, but we're in a little mechanical trouble, which need not fret us too much. Now, consider the following. Incredible device. A Leyden jar, dissectable, meaning I can take it apart. Metal, insulator, metal conductor. I am going to charge it on the Van de Graaff, storing some electric energy in this vessel, if you will, please. Enough? I'm going to show you that there's some electric energy there. Watch now what happens when I connect the outermost and the innermost. Watch it. Oh, and there's always some more. There it is, and always some more. So we have found evidence of storing some electric charge in that vessel called a Leyden jar. L-E-Y-D-E-N, Leyden or Leiden, after Holland. Peter von Muschenbroek discovered this. Indeed, he had a shock which so stirred him that he said he would not take such another for the whole kingdom of France. Now, I want to show you something very remarkable about this vessel. I'm going to charge it again, please. Enough? Now I am going to disassemble it. There it is. I have disassembled it and connected all the parts. Would you not think that I have discharged the instrument? After all, I've connected the outermost and the innermost. Watch me now. I now assemble it. And now watch. Watch. Ho-ho! That's a killer. That's a killer. I remember when I first saw this 50 years ago, it puzzled me nearly to madness because I didn't understand it. And so I suggest that those students who understand this, they deserve an A in this subject of electrostatics. I'm going to do that again so you'll see that it's no fluke. Again, if you please. Thank you. Notice, the greater the charge on the sphere, the greater the charge on this, and I feel the hair on my arm standing on end, and pretty soon I might have it. So watch, I'm going to disassemble it. I'm going to disassemble it. Notice, with absolute abandon. No, absolute abandon. Assemble it. Outermost. Innermost. Watch it now. Watch it. Uh-huh. The energy is still there. And I want to know how it is that rascal works. Now, I have another one. A bigger one. This is a glass vessel, which is coated on the inside with a metal foil, so it's a conductor inside. It is coated on the outside with a metal foil, so it's just like that dissectable Leyden jar that I had a moment ago, but this one cannot be dissected. Parenthetically, you notice I pronounced the word dissected, not dissected. It is not dissection when you cut up fishes and mollusks and cats and things. The word is dissect, and the word is also bisect, but not dissect. Watch me. I'm going to store some electric energy in this. If you will, please hold it, hold it, hold it. Now, if you will, please. I would say that's enough, thank you. And I think there's enough electric energy in here to knock down a horse. Watch. I'm going to connect the innermost and the outermost. Watch, watch, watch. Oh, Mother, that is incredible. That is something. I would say that could knock me down once more, because it's very dramatic. Once more. Oh, hold it, Nellie. I feel the hair on my arm standing on end. I feel my eyebrows beginning to tickle, which means that I'm getting loaded with electric charge. And now watch the energy in this system. Incredible. Watch it now. Watch it. Oh! As we say, a beautiful... I'm going to be sure. A capacitor, a Leyden jar, discharges exponentially, which means there's always some there, and one should never take a risk with it. Do you understand why it was that Peter von Muschenbroek, playing with these things in the 17th century, said, having taken a shock, that he would not take such another for the Kingdom of France? So we have explored some wonderful adventures in electrostatic phenomena, and all we have done is a little work separating positive and negative charges, and a whole new world is exposed to us. And I thank you for watching. How do you do, ladies and gentlemen, and teachers, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today, I have entitled Adventures in Magnetism. This is a marvelous subject because it is filled with enchantment and with many things we do not understand. As you know, there exist in nature some things which are naturally magnetic. For example, iron, nickel, cobalt, magnetic abundantly, highly magnetizable. But an added phrase, everything is magnetic to more or less degree, because magnetic phenomena have their primordial origin in the motion of electrons. And since atoms of all kinds of stuff have electrons which are in motion, everything is magnetic. So everything can be magnetized to more or less degree. Some things very slightly, of course. Just as everything can be electrostatically charged, some to more, some to less degree. Question, how can I make a magnet? Here is something that will enchant your soul. I have an iron bar. Iron is magnetizable. It is magnetic stuff. Let me say that this has no magnetic history, none. I'm going to magnetize it. I will put it in this place, in this room, in a north-south magnetic meridian, which is determined by a compass needle here. Here is a compass needle which points north and south. Somebody says, well, it doesn't point north and south, Professor, in this room. No, it doesn't, because I've got lots of alien and foreign magnetic influence around. But supposing this is the north-south magnetic meridian in this room, which it is, I'm going to take the iron bar, hold it horizontally, tip it a little. Now, why do I dip it or tip it? Because here is a needle. If we can get a look at this one, there is a needle which shows a magnetic dip. That's it. Not too reliable in its reading here and now because of the alien magnetic influences all around, including the magnetic personalities in this studio. Now, what was I about to say when I was diverted here by this phrase? Yeah. So the Earth's magnetic field has a horizontal component and a vertical component, and that's why I'm going to do this to the rod. And then with a hammer, I'm going to strike it smartly, as the British would say. Bang, 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 bang. And I have made this bar a magnet. I have magnetized it. Proof. Let me approach one end of the bar to that needle. Watch. Watch. Uh-huh. It repelled the needle. And repulsion is the only evidence that a sample of stuff is magnetized. Attraction proves nothing. So I've made a bar magnet. I made a magnet out of striking an iron bar. How else? Supposing I take a bar of iron or other magnetizable stuff, wrap a coil of wire around it, and connect the coil of wire to a difference of potential, such as a storage battery, I make an electromagnet. Here I'm going to do that. I have a battery, I have a wire, I'm going to wrap this bar with the wire, coil of wire. I will show you that this is a feeble magnet from my earlier adventure. Whoop, feeble, notice, no action, no action. Now I'm going to energize the wire with an electric current and watch the effect on the end of that rod. Watch it. Aha. And what else? Oh, the wire's getting pretty hot, sure. So I have made a magnet by striking it. I have made a magnet by energizing a coil of wire. Another. Here's a bar. Here's a hunk of stuff. Magnetite. Oh, that raises a very good question. Magnetite is Fe3O4. And so I like to ask, what is the valence of oxygen in this? 3 ions, 4? Oh, that's a good question. But anyway, going to make a magnet. This stuff has astonishing properties. Lodestone, it's called. Hang it up on a string, and it will set itself in the Earth's north-south magnetic line. I'm going to make a magnet out of this bar, which has no magnetic history. Watch me. Somebody says that looks like something mystic. In fact, regarding the hitting of that iron bar, or this business that I'm doing here, if I did that in my native New England in the 17th century, they'd cart me off to a stake for madness. But anyway, I make this an iron bar by stroking. Or, consider another better way. Here I have a bar that has been magnetized. Somebody says, that isn't a bar, Professor. Sure it is. It's a bar whose ends have been turned up, and it's a magnet. Oh, notice. Notice the motion. This is the direction of the magnetic field that emanates from this rod being magnetized. So I can make a magnet in many different ways. Problem. Here is a bar of iron, magnetizable stuff, which I have scored a little bit with a file so that it's breakable. Now, you know that if I have a horseshoe magnet, a bar magnet, it has some definitive regions called poles, south and north. If I break that bar magnet, as I have done here now with one already, we discover that each one is a magnet. So I have south, north, south, north. Supposing I took a piece of stuff, magnetizable, which has no magnetic history, and I make a magnet out of it. Let me do that. Watch it. Good. Now, here's what we have. we have a bar of stuff with some such polarity defined. Now I'm going to break it. And what do I have? A north-south, a south-north. I ask, what is the pole strength of these separate pieces? Very good question. Another adventure in magnetism. I have here two identical bars, absolutely identical in every respect. Same thickness, same length, same stuff. But I assert that one is a magnet and the other is not. And I can't tell which one is. Question, without any accessories whatsoever, no string to hang it up so it'll set itself in the Earth's field, no compass needle with which to test it, no pins or nails to pick up, how can you tell, just by the interaction of these two, which is the magnet and which is not? Let me show you the dilemma. A, B. They stick. Stick. You get the idea. They stick. They stick. Going to turn that one around. Stick. 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 Question. Just by handling these two, how can I determine which is the magnet? If I were a kindlier fellow, I'd give you a hint, but I won't. Wonderful little question. Next question. Iron is magnetic. Steel is magnetic. Nickel is magnetic. Cobalt is magnetic. Question. Is stainless steel magnetic? Is stainless steel magnetic? Oh, watch it. Piece of stainless steel. Horseshoe magnet. Very strong. Watch it. Well, notice. I don't think I'm going to show you because I think it's a very interesting question to leave unanswered. Is stainless steel magnetic? Well, I'm a kind fellow, so I'll show you. Watch it. It is not. Now, supposing I wanted to provide some magnetic shielding. Here is a sliver of steel, which is highly magnetic. Watch it. Sure, highly. Notice the influence of the field at quite a distance. I'm going, whoop, notice, you can't live with immunity in the midst of this stuff. I'm going to put a piece of zinc on there. Is zinc a magnetic insulator? No. Is copper a magnetic insulator? No. Is aluminum a magnetic insulator? No. Is wood a magnetic insulator? No. Is lucite a magnetic insulator? No. Here is a piece of iron. Iron is magnetic. Watch it. Sure. Let us see if this is a magnetic shield. Watch it. Watch. No, not a magnetic shield. Remember how thick it is. Watch it. Here is a thicker slab. Watch it. Oh, that's magnetic, all right. Is it an insulator? Watch, because this is tricky. Watch it. Oh, it looks like an insulator. I'm going to do it again. Watch me, because I'm sly and tricky. Watch it. No, it's not an insulator. I am raising a very exciting dilemma. Here is a heavy slab of iron. Is it an insulator? Watch me now. Very cautiously, watch me. I'm going to show that it is an insulator. Yeah, it's an insulator. Didn't pick that up. Now I'm going to do it again. I'm going to show that it is not an insulator. There it is. I want you to worry about that, and that's why I'm not saying anymore. Question. Supposing I had a bar magnet here and a bar magnet there, and I sprinkled some iron filings between. Let's go down here and see that. I have that very thing here. Here is a bar magnet. There is a bar magnet. I put a glass plate on top. I'm going to sprinkle this with filings. Look at the beautiful array that results. Beautiful thing. Now, supposing I had a bar magnet, N there, the S over here, and S here, the N over there. I have a strong magnetic field there. I want to insulate that region. How could I do it? Beautiful. If I sprinkled iron filings there, they would take such a direction. If now I put a heavy iron washer in there, we would find an interesting thing, that the field inside there would be field-free. The region there, field-free, meaning that soft iron is a very good magnetic insulator, which is an exciting thing to recognize. Now, some magnets, ceramic, discs, watch it. One, watch. They are polarized facially, and obviously light poles are adjacent, and you see that I have them running on an aluminum rod. It could not be magnetic. Are you not agreed that these magnetic phenomena are enchanting to witness? And I thank you for watching.